In modern warehouses, robots are used for stacking packages. However, the stacking rules are often hard-coded into the robot, which can be tedious when there are many different sized packages. Our project aims to simulate a box stacking system using Markov decision processes and reinforcement learning methods, and to learn the optimal strategy for stacking different sized boxes as stable as possible while minimizing the gaps between them. Given a fixed world width and a list of boxes of random dimensions, we want to determine the best policy describing the order in which to choose the boxes and the X location to drop each box at. Note that we're simplifying our problem to a 2D space with integer locations and dimensions. Our baseline follows an intuitive policy that consists of two rules. First, grab the boxes in order from widest to narrowest and tallest to shortest in case the width is a tie. This rule favors stability as it is likely for wider boxes to end up closer to the bottom. Then drop each box at a location such that the bottom of the box ends up as close to the ground as possible, favoring stability. If there's a tie, choose the leftmost out of the locations, favoring small gaps. I'll walk through a visualization of our baseline. At the very end, we will calculate a reward based on the stack's overall stability and gaps. The reward function will be explained later. For our main approach, I will describe how we modeled our MDP and briefly touch upon the Q-learning algorithm. Each state is a tuple with 3 elements. World is a 2D array of zeros and ones representing the current stack, 0 meaning the space is free, and 1 meaning the space is occupied. Box list is a list of width-height tuples of the remaining boxes. Pick box is either none or the width-height tuple of a box. As you may have noticed, we've been modeling our task as a sequence of pick, drop actions. An action can be either pick at some index of the box list or drop at some X location of the world. The success and probability reward function gives us a set of transitions to new states, each with a probability of 1 and reward, which is 0 in most cases. After each drop, we have a function that checks whether or not the stack goes out of balance based on whether or not the gravity of center of the box is protruding. If the stack falls, then we end the trial with a reward of 0. Otherwise, we move on to the next box. Similar to the blackjack homework, we don't calculate the reward until the very end of each trial. This end returns true either when the world is none, meaning that the stack has fallen, or when we've run out of boxes. Here's the flowchart of one trial simulated on the MDP. As a simple example, let's say we start with a list of 2 boxes, a 2x1 box and a 2x2 box. We could pick the box at the 0th index, which is 2x1 box. Then we could drop it at the X location of 0. And the only box left is the 2x2 box, so we'll pick it. And we could drop it at X location of 1. Now we've reached an end state, and we will calculate the reward based on the ending stack configuration. This is a high-level version of our reward function evaluated on an ending stack configuration. We start with a constant proportional to the number of boxes, in this case 5, and we penalize 2 metrics, instability and misalignment. Instability relates to the gaps in the vertical direction, and misalignment relates to the gaps in the horizontal direction. Stacking boxes is an online task. In the real world, the robot doesn't know how the world works. For example, whether or not dropping a box at a certain location would cause the current stack to fall. With reinforcement learning, the robot learns the optimal policy by performing actions in the world to find out and collect rewards. Based on our defined MDP, our reinforcement learning algorithm utilizes epsilon greedy and Q-learning outlined on this slide. I won't describe the specifics of epsilon greedy and Q-learning because it's just what we learned in lecture. We've generated random box lists containing 3, 4, or 5 boxes with random width and height between 1 and 3. Besides the box list size, it's also interesting to test the algorithm in spaces with different widths and world sizes. Using a world width of 3, 4, or 5, we have 9 total situations in combination, and we ran 30 rounds of simulations for both the baseline and reinforcement learning algorithm and recorded the average reward for each setting. We see that the reinforcement learning algorithm performs better than the baseline as the width of the world and the number of boxes increase. Whereas the baseline performs better when the number of states is small. The biggest challenge that we faced was the huge number of states. We made the world discrete, which helped, but there's still too many, and the program runs super slow when the number of boxes becomes 10 or more. In the future, maybe we could try simplifying the world space from a 2D array to a 1D array. Also, we've noticed that this MDP is actually just a search problem because the transition probabilities are always 1. But we still decided to keep the MDP structure so that it's flexible if we eventually decide to add uncertainty. For example, a box might be crushed or damaged with a random probability. We had a hard time defining stability. Currently, it's just based on the vertical gaps, but we could improve by incorporating physics simulation. And finally, we simplified the problem a lot to reduce the number of states. In the future, we could try to find ways to make it more realistic. For example, by considering the box weight, and maybe a stack would fall when heavy boxes are at the top. And that's the end of our video. Thanks for watching.